22,000 years ago, Earth had an average global temperature that was 6 degrees cooler than today. Right now, ice covers 10% of Earth's land mass. 22,000 years ago, glaciers covered 25%. All of that water trapped as ice caused sea level to be 410 feet lower than it is now. Enormous animals roamed the grasslands. You had dire wolves, glyptodon, woolly mammoths, and saber-toothed cats. What caused the glacial period, and why did some animals survive the change to a warmer climate, while others did not? I'm Science Mom.
I'm Math Dad.
Today we're exploring ice ages. Hello, everybody. Give us a quick thumbs up if you can hear us in the chat, because we had a computer crash right before we were supposed to go live, which was really stressful, and we aren't sure if everything booted up okay. So I just need to see thumbs up. Can you hear us? Do we have audio? I see Kat says hi. Finn W, hello. Savannah says, "Ay caramba."
Science Mom Jamie gave us
We
a
can
thumbs
hear
up.
you. Oh, good. We are glad.
My guess is that a lot of people are kind of cold this morning, or have been for the last few days.
It might feel like an ice age where you're at. Let's look at a map of the United States right now showing the temperatures, because they are much cooler than normal. And before we start talking about ice ages, I wanted to talk about the current weather forecast that is happening, because we've had some record low temperatures all across the United States. And what we've learned about in weather can help explain this.
Ooh, I'm curious.
So remember, we talked about the Ferrel cells and the Hadley cells. We have these regions of air that are circular, where you've got these massive currents coming together.
Cycles that were happening.
Yes.
Right?
And it turns out that with the Ferrel cell especially, we've got this rotating column of air here. And anytime you have a difference in air pressure, air is going to flow from high to low.
Right.
And when air flows from high to low here, in between these two cells, because of how the Earth spins, we get a jet stream. So this fast-moving air current up here, when I say fast, it's going more than 100 miles per hour. This is the jet stream.
So that's where the polar cell is meeting the Ferrel cell. That's taking the air way up high, and that's what we call the jet stream.
That is the jet stream.
How high is that? Is that still in the troposphere?
It's still in the troposphere, but it is up close to the top of the troposphere. And this jet stream, if it is circular and strong, then you have all of the cold air contained up here near the North Pole. But if the jet stream becomes weak and wavy, then you'll have a huge amount of cold air that will move down to lower latitudes.
Is that what's happening right now?
That is what is happening right now. And I see several people commenting that it's laggy and glitchy. I apologize. Hopefully the recording will be good. I think because of all of the power outages and things that have happened this week with the cold weather, we might be having some bandwidth issues just nationwide.
Yeah. Fingers crossed that it will improve.
Fingers crossed. So let's take a look at one of my favorite websites. We're going to go to earth.nullschool.net and talk about what the polar vortex actually is. Because sometimes in the news, people use that term and they're not talking about the stratospheric polar vortex, but this is the stratosphere. This circular band of air is the polar vortex. This is the jet stream. This is in the troposphere. And these two things can influence each other. If the polar vortex gets weak, then cold air will descend from the North Pole down south.
Gotcha. All right, so what are we seeing here, Science Mom?
So this is this cool website, which is showing us real-time data of what the wind speed is like right now.
Earth.nullschool.net. I'm gonna paste that into the chat because I think a lot of people will be interested.
All right, Math Dad's putting it in the chat real quick, and I'm happy to hear from a couple people that it's not laggy. Fingers crossed that our quality will improve as we go. So this is a map of the world, and if we look at the temperature, then that will tell us exactly where our troposphere and stratosphere boundary is. Do you remember that?
So this is showing
difference?
live? Or,
This is live.
Approximately live?
Yes.
Oh, that is cool. So the troposphere is on bottom, and in the stratosphere, warmer than the air below, ozone layer had a hole.
That's
Airplane
right.
contrails white like snow in the stratosphere.
So let's look at the surface. This is the surface. And if we look at the surface right now,
oh, you can totally see the cold temperature.
The cold temperatures
almost down to Mexico.
Over the US. So when it gets blue, blue means that it's close to freezing, and the green is above freezing. So you can see the temperature is really cold. Watch what happens though as we go up higher. This is kilopascals, but it translates to altitude. It's pressure. And as we go up higher, it's getting colder and colder and colder. And this is the top of the troposphere, which is, look at that temperature, negative 60 degrees Celsius.
Oh my goodness.
But now if we get into the stratosphere,
oh, it got a little bit.
It is warmer. It's warmer in the stratosphere. And now let's take a look at what the jet stream is doing right now. So I'm going to go from temperature, we're going to change over, we're going to go back down to the surface real quick and change to wind. Here is the surface wind right now, and you can see it's windier over the oceans than it is over the land.
And is that usually the case?
That is usually the case. If we go up to the top of the troposphere, you can see the jet stream, and the jet stream is moving incredibly fast, and it's coming all the way down across Texas. Usually it's up near Canada.
Oh, and that explains this cold spell.
And that is the cold spell. And if we go up to the stratosphere, this is not as strong as the vortex usually is. Usually the vortex is white, and usually it's up a little bit more centered over the North Pole. It's down a little bit lower. In any case, you can tell the stratosphere is a lot calmer and more organized of a place than the troposphere. So here in our stratosphere, there's really just like two main directions that the wind is going. But if we come back down to the troposphere, look at all that chaos.
So when in the songs, all our weather happens here, and it's really because in the troposphere, that's where we're experiencing all this.
Exactly. Now we'll stop. All right. Sorry, you guys. That computer crash right before we went live was really stressful and kind of threw everything off. All right. So
it's starting to get cold. That means we must be going into an ice age.
We are not going into an ice age. And this is a common misconception that people have. When people hear ice age, they usually think of what is a glacial period. We're actually in an ice age right now. So let's define
what?
Let's define what an ice age is. An ice age is a period during the Earth's history where you have large amounts of ice. And then in between ice ages, we have periods where there is no ice. So here, there was virtually no ice on planet Earth. And then during an ice age, you got ice at the North Pole and South Pole, and the poles were way, way colder than the equator.
Okay, so you're saying this is a timeline of Earth's history going back like 4.5 billion years. And you're saying went all the way to here, then there was an ice age? Okay. And,
yes.
Okay, that is crazy. Then, so the ice ages were those blue ones.
The ice ages are the blue, and you can see before the dinosaurs. So this is the entire dinosaur age, from first dinosaur to last dinosaur. We had 4 different ice ages before the dinosaurs. And then after the dinosaurs, we had another ice age, and it's the ice age that we are in right now. So if there is ice on Antarctica and ice at the North Pole, that means we're in an ice age. But during an ice age, you have glacial periods and interglacials. And during a glacial period, the ice sheet gets way bigger. And then during an interglacial, the ice sheet gets a lot smaller. But both of these are ice ages. Math Dad's trying one quick little fix to see if that might help. So we'll see if that helps. Yep. Sorry again about the connectivity issues.
That's the North Pole you're looking down from, right?
Yes, this is the North Pole.
So currently, the one on the left is the current state?
Yes, we are in an interglacial period right now. This is the North Pole right now. And 22,000 years ago, the North Pole looked like this. And you can see that the land changed. Japan was connected to the rest of Asia during this time.
Whoa.
And I have a quick little demonstration that we can do, Math Dad, to show why this happened.
All right.
You ready? So here is a bunch of blue water, and I'm putting in some ice cubes.
No, you're not making any mess, right?
I'm not going to make a mess, Math Dad. Don't worry. And here is the ocean level in our little mason jar world.
Okay.
And if we enter an ice age, then water is going to be going up into the atmosphere, freezing into ice, and then snowing down on a continent.
So that's just taking the water out of the ocean, essentially.
Taking the water out of the ocean, and our water level is dropping.
Yes, it is. It used to be up here, and now it's down about an inch, a couple centimeters.
Put it a little closer so they can maybe see that mark. So our water level was up here, and then when all that ice rained down on the continent, the water level dropped. And the same thing happened to our oceans. If we look at a map of Florida and a map of Asia, then you can see that the coastline now looks very different than what the coastline looked like 22,000 years ago. 22,000 years ago, Florida was 3 times bigger. And 22,000 years ago...
Wait. So the map on the left is the current map, the green.
Green. The green is what our coastline looks like now. And the purple is what it looked like 22,000 years ago.
So that's Florida dangling down there. And
yep,
the Gulf of Mexico was a lot smaller.
It is. And over here you have Indonesia, most of it being connected in one big landmass. And then Papua New Guinea was connected to Australia.
Whoa.
And there was a lot more land there. And this is not going all the way back to Pangaea. This is just 22,000 years ago. It's pretty recent history. This is during the last glacial period of our ice age. And during that glacial period, we had huge glaciers that carved out valleys. This is Yosemite, and Yosemite is a very famous U-shaped valley. This whole area was carved by a glacier running down. And this valley here was also carved by another glacier that was entering this big one. And that's why you've got this cliff face here.
A glacier, right?
There were glaciers down Yosemite.
When you say the ice doesn't move, right?
Oh, it does.
Glaciers are stuck in place.
Glaciers flow just like rivers flow.
So like really slow rivers?
Slow, powerful, heavy rivers. They are slow, they are powerful, and they push massive rocks as they go and really erode things. Another evidence of ice ages are the incredible fossils that we have. So the woolly mammoth is one of the most famous, and these animals had very thick fur coats to help them stay warm, and they were enormous. If you look at the woolly mammoths compared to people, they were huge.
But were they bigger than elephants?
Yes, they were bigger than our modern elephants. And in addition to large elephant-like creatures, we also had Glyptodon. It was an armadillo pretty much the size of a car.
It's almost like a dinosaur.
It weighed as much and was about the same size as a Volkswagen Beetle car. So just enormous. And then the giant ground sloth, Megatherium, was another prehistoric ice age animal that roamed all over America.
So these ice age animals were huge. Is that because it was cold? Or what? Why were they so much bigger?
There are different theories about why they were so much bigger, but one theory is that it did relate to the cold temperatures, because if you are big and you have enough food to maintain your energy, you're not going to lose heat quite as fast as if you're small.
Mm.
And where you have big herbivores, then you are also going to have big carnivores. And the saber-toothed cats are a really famous example of an ice age carnivore, but you also had dire wolves, and these animals were fast.
Oh man, so look at the size of those teeth on that thing. Like, would they even be able to get the food in their mouths? Like, that is crazy.
They had enormous teeth, and it must have, it's thought that that was used probably in the way it attacked, because it's not super practical for eating.
Doesn't seem like it would be. I gotta say, I would be scared out of my wits to see one of those things in the wild, though.
That would be terrifying. Now, sometimes when we think of the glacial period, we just think of these animals that went extinct. But there were a lot of the animals that we see alive today were around during the last glacial period, including trees like the aspens. The aspen trees, one of my favorite trees. And if you look at where they live, do you think they like cold weather or warm weather?
They definitely like the cold weather. They're all up in Canada for the most part.
They definitely do like cooler weather, but we have some aspen trees growing right where we live in Nevada, up on the tops of this mountain, and then down here on the top of this mountain. How can these aspen trees live on the tops of different mountains when they don't make very good seeds? Their seed germination rate is terrible. Most of their reproduction is the tree will send out roots that travel along the ground, and then up comes a new tree.
Oh, I was going to say that they just had lots of seeds and the wind blew them, but you're saying that doesn't
work. That doesn't work for aspens. And it's because during the last ice age, the aspens all lived down here. And the mountains were covered in ice, but as the ice receded and as it got too hot in the valleys, the trees just moved up into the mountains.
Oh.
Pretty amazing, right?
And so throughout the Rocky Mountains there, so you're saying that's where the aspen groves are, is wherever the mountains are at.
Yeah.
Because the mountains are colder.
Yep. And now they only live at high elevation down in this whole area. They're just in high elevation.
But if you go up to Canada, they live at lower elevations.
Yep.
Gotcha.
So those are just a few of the evidences of ice ages. But a really good question is, how do we even know what the temperature was 100,000 years ago?
So a quick question did come up in the chat. So what exactly is a glacier again? Because you said it was somehow like water that's moving rocks and things. Can you just clarify real quick?
Yes. So a glacier, and we have a whole section once we get to hydrology where we'll have a class just on glaciers. But a glacier is pretty much a river of ice. So when you look at a piece of ice, you might think to yourself, well, that's totally solid. But what if you had 1 million pounds on top of this ice? It would slowly flatten out, right? Well, a million pounds, it might just like go crunch and be gone. But if you have enough weight on ice, the ice will slowly move and deform. And that's what happens with a glacier. It's a river of ice that is so big that the weight of the ice behind and above it will push it slowly downhill.
So when you were showing us that canyon in Yosemite, you're saying there was a giant ice cube essentially that pushed down and kind of carved out that valley?
And carved it out, yes.
Over thousands of years, hundreds of years?
Hundreds of thousands of years, millions of years, over a long time. Yeah, good question. Now let's go back and look at this picture right here. And these are fossilized remains of microscopic animals. And in the ocean, you have plankton and different animals floating in the water. And some of them like warmer waters, some of them like cooler waters. But after they live, their little skeletons fall down and land on the mud. And by looking at the layers of mud in the ocean, if you go, it's like looking at the pages of a book and going back in time. Each time you go down to a deeper layer, you can tell like, oh, here was a volcanic eruption and laid down ash. And ooh, this lighter area, the water was warmer. This darker area, the water was colder. You can tell what the weather was like by looking at these sediment layers. So ocean core sediments and looking at what type of little microscopic animals are in the sediments, that's one of the main ways that we know what the weather was like so many thousands of years ago.
The one on the right is just coral, isn't it?
This isn't coral. This is a tiny microscopic, fossilized microscopic animal.
Oh, they just zoomed in way.
Yeah, it's an electron microscope picture, so it's really zoomed in.
Oh, cool.
And here is a map of our glacials and interglacials. So I said that 22,000 years ago, there was a glacial period where most of Canada and the northern part of the US was covered in miles of ice. Ice glaciers and ice layers that were more than a mile thick.
How do they know that? Because you just showed us a slide where they could kind of measure from the seas, but...
So how do they know that? There's lots of evidence. You have valleys that were carved out by the glaciers, lines that are grooved in the rocks from the glaciers.
How do they know it was 22,000 years ago?
It's like putting together a puzzle. So they know it by gathering lots of different data and then matching it up. So from ice cores and from calculating, how long would it take for the ice to recede? And also the ice was so heavy, it actually pushed the whole continent, kind of pushed it down. And our continent is still sort of rebounding from all of that weight. And when Europeans first came to New England, there were no earthworms in the soil. because it had been covered in ice recently enough. The earthworms hadn't migrated back yet. Earthworms migrate very slowly.
Whoa. Whoa. That is crazy to think about. Yeah, obviously worms are going to go slowly. And you're saying there were no earthworms because the ground was...
Because it was recently in a glacial period.
And earthworms don't live in frozen ground.
No, they don't.
Whoa, so that's really recent.
Well, recent geologically,
yeah.
22,000 years ago is recent geologically, but
you're saying when the settlers arrived, Pilgrims, 1620.
Yeah, they thought it was really weird. They're like, how come this ground has no worms? Worms are important. And they got worms and brought them and said, all right, now we have worms in the soil.
Wow, so the worms are slowly migrating north. That's really crazy to think about.
Yeah, it is. All right, let's go back to this picture because I want to talk a little bit about how an ice age starts and ends. But more importantly for us, how does a glacial period start and end? So here,
because I missed this earlier, but we're in an ice age right now, is what you're saying.
We are in an ice age right now.
It's just the interglacial part, so where the glaciers have receded a bit.
Yes.
Okay.
So we're in an ice age, but we are not in a glacial period. So these are glacial periods. So this is when the temperature is colder. And then these are interglacials, where the temperature is warmer.
Well, okay, so you're saying this black line in the middle is the temperature line?
Yep, and you can see that temperature line, that changes a lot, up and down. It changes a lot.
As many as 5 degrees up or down from that average is what I'm seeing. Yeah, is 5 degrees Celsius.
And part of the reason that we get these interglacial and glacial periods is because the Earth is not going around the sun in a perfectly circular way. And our tilt of our planet also changes and wobbles just a little bit. And those things cause our ice ages, not our ice ages, sorry. They cause our glacial periods to come and go.
Because again, warmer versus colder over time.
Warmer and colder, because the amount of radiation we get is going to change. So if we're looking at how much radiation we get from the sun, you can see that it's a pretty regular up and down. Sometimes we get more, sometimes we get less. And it's like every few thousand years, it's changing up and down. But the glacial periods, they're not matching exactly with it. And there are still some mysteries about what exactly causes a glacial period and when it happens and when it ends. But you'll notice that
it would have to cool down for a long time to get sustained cold to form those glaciers, right?
Yeah, it takes a while for those to form. But when we go to an interglacial period, look at how steep that curve is. That happens pretty fast.
Oh, so you're saying they start fast?
Yeah, so a glacial period, it starts slowly and it ends abruptly.
Oh.
So it takes a while for it to start and get cold, but then once it warms up, that warming happens pretty fast.
Oh, I see. The warming is what was happening fast. All right, and what's that bottom curve?
That's carbon dioxide. And we'll talk more about this next week, but carbon dioxide matches the temperature pretty closely.
Well, those two graphs look almost identical. Just move one up and you've got the other one.
They're not exactly identical. See, there's a little peak there and there's not one here, but they're pretty close.
So it seems like you can use that bottom graph, the amount of carbon dioxide, to predict the temperature a lot better than you could use the sun in the top graph, right?
Definitely. Let's talk about positive and negative feedback real quick, and then we're gonna go to the notes, and then we'll have our poll questions. So positive feedback, you might think is just like, oh, someone gave me a compliment.
So positive feedback's good.
Well, in biology, positive feedback means that you get more of what you started with.
Okay.
So if you have one ripe banana, that ripe banana that's starting to get ripe is going to produce ethylene gas. Okay. And ethylene gas is going to make the banana ripen even more. So it's a positive feedback loop because ripeness gives you more ripeness.
Wait. So once it starts to get ripe, it's letting off more ethylene?
Yeah. Have you ever noticed if you have a bunch of green bananas, they'll be green. If you get really green ones, they'll be green for a while. And then when they start to get brown spots, they go fast.
I have noticed
they'll go from being perfect ripe to way too ripe and only good for banana bread, just like that. And that's because of a positive feedback loop. And have you heard the saying, one bad apple can rot the whole barrel?
Yes.
That's an actual fact. Back in the day when people would store apples for the wintertime, if you had a barrel of apples and there were no rotten apples in there, all of the apples were unripe, they would last for months. But if you had one apple that got ripe and then turned rotten, just one of them, it would make enough ethylene gas that then the entire barrel would go rotten.
Oh, I had no idea that was an actual thing.
Yeah, within just like a week or two. And it's because of a positive feedback loop. Anytime in biology we have a positive feedback loop, that means that things will change pretty quickly.
Wait. So a positive feedback loop is not a good thing in this case?
It all depends. If you're trying to make banana bread, then that positive feedback loop is really nice because you don't have to wait so long to get banana bread, bananas.
But it's positively correlated with growth.
Yes. So. Positive feedback loop equals you're going to get change. And negative feedback is the opposite. And let's look at this slide here real quick. One example of negative feedback is when you get hot, you sweat. And if this was a positive feedback loop, then getting hot would make you sweat, sweating would make you hotter, and then you'd combust into a fireball.
Yeah. You'd sweat more, and then you'd get hotter, and you'd sweat even more, and you'd get even hotter. Like that would be
terrible. But fortunately, sweating is a negative feedback loop. When you sweat, that cools you down and gives you less of the heat that started the whole process.
Oh, I never knew I liked negative feedback. Crazy.
So with our climate and with ice ages, there are several positive feedback loops. And if you want to test one of them, get a piece of ice and put it in a bowl, 2 pieces of ice. And one of them has white on top and one of them has dark construction paper. You can see that this is starting to get just a little bit of a wet spot from melting. If we put these both outside, which one do you think will melt faster, Math Dad?
Oh, I have a theory. I think the dark one will because it absorbs the heat better.
Yes. If you have dark colors, that absorbs heat and gets warmer. If you have white reflects heat, and this will stay cooler, and this ice will not melt as fast. With ice ages and glacial periods, once you start to get ice, it reflects heat and makes the area colder. And then if it's colder, you're going to get more snow and more ice, and it's going to reflect more light. There's a positive feedback loop. And the same thing happens when the ice starts to melt. Once it starts to melt, you have dark colored ocean instead of ice, and that absorbs more heat and warms up and melts more ice.
Okay, that makes a lot of sense. We've actually tried this experiment before with a magnifying glass, trying to light a piece of paper on fire using the sun to focus the ray. And with white paper, it was really hard.
It's almost impossible if you just have white paper to light it with a magnifying glass. But if you have ink on the paper,
we've tried it. Yeah, we could totally succeed in bursting into flames. Yeah, it's really kind of a fun experiment to try because you just wouldn't think that it would make that much difference. It's just a little bit of darker color, but
it makes a big difference. It makes a big difference. All right, let's pull up the notes real fast. I want to show you an example of a single volcano that changed the weather over the entire planet.
So what page are we on here? This is page 39 of the notes.
Page 39. So when I showed you that graph where the solar energy was going up and down, this is the Milankovitch cycles, and it's caused by how round the Earth's orbit is and how much the Earth is tilting and exactly where the Earth is pointed to. And the little differences here can have a big effect. But the amount of ash in the atmosphere can also have a huge effect. Mount Tambora is located in Indonesia. And before its eruption, it looked like this and was a fairly big mountain. If you look at it now it looks more like this.
Oh, are you telling me that the top part of the mountain just blew away?
The top part of the mountain is gone. This eruption was one of the biggest eruptions in the recorded history. Mount St. Helens was a big eruption, right, Math Dad?
That was the one when I was a kid. This was 1987, if I remember right. Yeah.
And Mount St. Helens put 1/4 of a cubic mile of ash into the atmosphere. That's a lot.
Yeah, it is.
Krakatoa is another big eruption that put 4 cubic miles of ash into the atmosphere.
Oh.
This one, Mount Tambora, put 19 cubic miles into the atmosphere.
Oh, yikes.
And that is so much ash that it acted kind of like a shade cloth. If you go to a store like Home Depot in the summertime and you're looking at plants, a lot of times in hot climates, they have shade cloths over the plants so that the plants stay cooler. And you can tell a temperature difference. If you are just standing in the sun, you're really hot. But if you walk underneath a shade cloth, you can still see, but it's a lot cooler.
Yeah, it's not full shade because there's still ways for the light to get through, but less light is getting through.
So that's what happened with this volcano. It put so much ash into the air that ash acted like a shade over the whole entire planet, keeping less sunlight from coming in. And it caused what we now nicknamed the year without summer. So this happened in 1815. And then in 1816, in Pennsylvania, rivers froze in July and August. Every single month, there were really bad frosts. So it would be like the weather we're having right now across the US. Imagine that happening in July and August in the middle of summer.
Oh, no.
So there was massive famine. Crops failed all over Europe and North America, especially. And it was all just because of one volcano.
And that's clear the next year. So that ash stayed up there a long time.
The ash did. And one volcano or one nuclear war could actually cause the planet's climate to change for more than a decade if it puts enough ash into the stratosphere. All right, we had several really good questions. I'm going to look through our questions while Math Dad brings up our polls. So as usual, go to itempool.com/sciencemom/live, and we are going to see what you guys learned about ice ages. You ready?
Okay.
And we've got to do this a little bit differently because of our computer crash. So bear with us as Math Dad gets it set up. The first question is about how many ice ages there were in Earth's history.
Ooh.
How many major ice ages have happened since Earth has been around?
Oh, so if you were paying attention earlier, we did say this, but...
And I will say, if you just Google the answer real fast, you need to begin accepting answers.
Apparently, I have to accept answers.
You can do it, Math Dad.
All right.
I will say, if you Google this, you will find slightly different numbers. Sometimes they'll say it's a little higher, sometimes a little lower, but the most commonly agreed upon answer is the one we mentioned in class. So just type a number in.
And then I just got to ask one more time to make sure that I heard you right earlier. Are we in an ice age right now?
Yes, we are in an ice age right now because is there ice at Antarctica?
There's definitely lots of ice in Antarctica. Yeah.
Are the poles colder than the equator? A lot colder?
Yeah.
That means we're in an ice age.
Crazy. I thought ice ages were things of the past.
Are we in a glacial period right now?
No, you said it was interglacial.
We are in an interglacial
kind of
period.
Between the glacial periods. All right. Ooh, I think we might stump them on this one.
I don't know, Math Dad. There is one bar that is longer than the rest. I'm going to go ahead and finish and reveal. The most common number put in was 5. Good job, you guys.
5 is correct. So we are in the middle of Ice Age number 5.
Yes. Ice Age number 5 is the ice age that we are in right now. And sometimes people will say that there were 6 or 7, but the most commonly accepted answer is 5. That's best we can tell. There have been that many ice ages.
All right. Question number 2. Which of the following statements is false?
So only pick the false statement. If you read it and it's true, don't mark it. Only pick the false one.
Oh, you told them there was only one correct answer.
Oh, sorry.
Yeah. Science Mom and her hints. All right. So we are in an ice age right now.
Is that true or false?
A large volcanic eruption can cause global weather to become cooler. An ice age has glacial periods and interglacial periods. And most ice ages develop quickly and end slowly. So what do we have? Which of those statements is false? And I don't think they're going to get this one, Science Mom.
I think they are.
They can try their best, but we shall see.
All right, we're going to finish and reveal. Most ice ages develop quickly and end slowly is false. They usually develop slowly and they end really quickly. Remember how steep that curve was when it warmed? It warmed all of a sudden. Most of them.
Oh, that kind of makes sense. It would take a long time to build up ice.
It does. It takes a long time for glaciers to form. You have to have more snow coming year after year for that glacier to form and the ice age to develop. But when they warm, if it gets hot, you can melt like ice ages. You can melt glaciers pretty quickly.
All right. True or false? Antarctica used to be covered in lush forests. All right. I think they'll get this one right. Although I'll stump several of them.
In the chat, I'm seeing several like, go unbeatable science kids. Yep, you're not going to stump a Math Dad.
Yeah, true false questions. I need more wrong answers. That's what I need.
Here we go. True. This is such a cool fact. There are fossil records of enormous trees and dinosaurs that lived on Antarctica and also up at the North Pole too. So if you look at the very top of Canada and Alaska and Russia, there is evidence that there used to be plant and animal communities up there that were adapted to this really crazy environment where it was warm most of the time, but then you'd have light for 6 months and then dark for 6 months. So the trees would photosynthesize like crazy during the summer months, and then they would store all of that during the cold, dark months.
It's really weird to think about that the poles could be warm.
Yeah.
And that might be the more usual state of things on the planet, speaking geologically. Yeah. All right, well done. I still stumped a third of them on that one, though. All right, question 4. What caused the year 1816 to be so much colder that it was nicknamed the year without summer? Was it that the Earth moved further away from the sun? Was it that the tilt of the planet changed? Or a massive eruption of a volcano in Indonesia? Or decreased circulation of ocean currents? What do you think, Kaladin? What do you think? Yeah. Okay. You know what I think? I think they were listening. Got 90 votes for the correct answer here.
Good job. It was a massive eruption of Mount Tambora in Indonesia.
All right, and our final question of the day. Ooh, they would really have to pay attention to get this one right. During the last glaciation period, so going back 22,000 years, the sea levels were much higher or lower. Which was it?
You know what? I wondered why Kaladin was looking down so much, and it's because he can smell. Earlier when we were working on his commands, I had an extra treat that I put in my pocket, and I think he could smell it.
Yeah. You're such a good dog. Ooh, okay. Lots of people are guessing the wrong answer. I don't know whether it's the bigger of the two bars.
All right, finish and reveal. Let's see what they say.
Oh, they're going down, Science Mom. And they said that the sea levels were lower.
And they're right.
Oh,
good job.
They were right. And that was the demo you did with the ice.
Yeah.
So a lot of the ice ended up on the continents, so there was less water in the oceans.
Less water in the oceans because there was so much water up on the continents.
And that caused the sea levels to drop.
Yep.
Yeah, fascinating.
It is, it is. All right, Math Dad, you owe them a quick little victory dance.
Oh, man. All right.
Victory for the undefeatable science kids.
It goes.
And we have the chicken floss again. I did see a request for some pretty exotic dances in the chat. I want to answer several questions that came in. Great ones from Ailsa. During Pangea, were the temperatures different than they are today? Yes. During when all the continents were together in a supercontinent, which is usually called Pangea, temperatures were a lot warmer. There was not an ice age during that time.
So it'd be less hospitable for humans.
Yes, it's a climate that we would not enjoy nearly as much. What would happen if it's only one of the poles that is cold? That's an interesting question. It would not be possible for just one of the poles to be cold because they alternate their summer and winter, but they experience pretty similar conditions.
But having the continent, so down at the South Pole, does make Antarctica colder. We've seen that.
Yeah. Good question from SC. What type of microscopic animal is in the picture? Different species of phytoplankton or foraminifera. They're these tiny little animals that float in the ocean. And, great question from Cien Bryn. Says, I live on a hill and from my window I can see a valley and then mountains on the other side. Was that valley formed from a glacier? It all depends. If that valley has a U shape and if that valley has a big pile of rocks at the end that don't match the rocks that are all around, then probably it was, because glaciers, when they carve out valleys, they'll pick up rocks from one area, and then when they melt, they end up leaving rocks that don't match in other areas. But it all depends on where you're at. If you are in upper New York or the Midwest area, kind of up towards the north, like Minnesota, Michigan, then chances are pretty good that there is evidence of glaciers right around where you live. Could we clone woolly mammoths like in Jurassic Park? Good question from Remington Wolf. We actually do have complete DNA samples from woolly mammoths, and they've been able to sequence genes and match some of the genes in the woolly mammoths to genes in other animals and help, like they know what color their fur was. And they know all these things because they've been able to map the genes. But cloning an animal just because you have a section of DNA is still, that's very much more in the science fiction realm of things.
That's a good question, though.
And then good question from Mike Cool's MA. How does an ice age end? And it depends on the ice age that you're talking about, but it ends because of positive feedback loops. Usually you'll have some event that causes warming, and then once you have warming, if the warming passes a threshold where the caps melt and those massive ice sheets melt, then the planet absorbs more heat because the ice is not reflecting the light, and that will contribute to the ending.
And that will keep it warm because it's absorbing more heat over time. So that positive feedback. Gotcha.
Yes.
But yeah, there's definitely no simple answer to why they end. I mean, it's happened pretty abruptly, though, right? They end. For some reason, it warms up, the ice melts.
And then one last question, Adeline DIY, was the ice age after the dinosaurs? The ice age that we're in right now was after the dinosaurs. Yep. And it's the cooling that happened when that ice age started kind of contributed to some extinction events that led to where we're at today.
I always thought of ice ages as something of the past, but you're saying that we like ice ages because that's the climate that's
what we're used to.
Yeah.
And if it weren't for global warming and climate change, we would actually be getting ready to go into a glacial period. So within the next several thousand years, which is really soon, geologically speaking, then we'd be entering another glacial period where glaciers would get bigger and it would get a lot colder. But that's not going to happen because of the extra carbon dioxide that we've put into the atmosphere. We're not going to go back into a glaciation period. All right.
These are great questions.
They are really good questions. Last little fact, we said in our little intro video that some animals survived and some animals did not. And this is an interesting question, and it's one that's actually a bit of a mystery. So if you are interested in paleontology, I hope you might grow up to research this question, because we don't really know, why did animals like the pronghorn, the antelope, the American antelope pronghorn, why did that animal survive? But the saber-toothed tiger and the dire wolf, those animals went extinct. We have some ideas, but a lot of it is unknown. There are still mysteries and questions waiting to be answered.
That's fascinating.
All right, I hope that you guys enjoyed this lesson, and thanks for putting up with our crazy snafu at the beginning and the internet lagging.
So one from Corinne said, what are some of the animals or Amelia actually, what are some of the animals that survived from the last ice age?
Us.
So
last
pretty
glaciation.
The last glaciation, but it's everything that's alive now, for the most part, survived through.
Yes. So human beings, we survived the last glaciation period, and antelope, wolves, foxes, like pretty much any animal that you see alive today, its ancestors were alive 22,000 years ago and made it through that glacial period. Good question. And I did see a great question about marmosets and when marmosets, they were around too, because you still had tropical forests, but the tropical forests they were in a smaller band around the equator. So, but exactly as to where marmosets were during the ice age, I don't know. I'd have to research it, but great question. All right, you guys, work hard, grow smart, and we will see you on